Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. In this session, we have the privilege of shadowing a stellar team of astronomers. Zhuo Chen, a postdoctoral researcher at the University of Washington, and Raja GuhaThakurta, Distinguished Professor of Astronomy and Astrophysics at the University of California, Santa Cruz, and also the founder of the Shadow the Scientist initiative. Now, Zhuo and Raja, along with their colleagues, plan to use the Keck I 10-meter telescope and the OSIRIS instrument to study the kinematics and chemical composition of stars that make up the nuclear star cluster of the Triangulum galaxy. Now, observations are already underway at the Keck base facility in Waimea, which is on the northern part of the Big Island. Raja has just joined us, and so let's check in with him to get started. Raja, welcome.
Hi, everyone. Welcome. Hi, Vicky. Let's see. I'm just getting ready to share my screen. Can you all see my screen?
Yes.
And that big gong you heard has to do with instrument notification. We're just getting on our science target. So I'm going to show you some other screens as well. We're just getting ready to start our science target. That's our science target right there, the nuclear star cluster. And we're just getting ready to, remember yesterday we had it on the right edge. Today we have it on the left edge.
I'll let you decide. Okay.
That looks good. Sure.
Yeah, I think it look good to this film.
Yeah, that looks good. That looks like that, yeah. So we put the star cluster on the left edge of the field of view. And, but I wanted to also show you this screen. This is last night, an image from the Subaru all-sky camera. This is the Keck I telescope. I'm going to show you the annotations with and without. Keck I, Keck II, you can see the domes. This is the sodium laser shining out of the Keck I dome. That's Jupiter right there. There's Sirius about to set, or maybe it was rising, I can't remember. Must be. And there's Orion, the belt, sword, head, shoulders, Orion the hunter. So these images were captured from the television monitor, but the Subaru camera has a live stream, a YouTube channel where live streams. If I can find it, I can send you that link. So tonight it's showing a very similar image, Keck I, Keck II.
I'm gonna eat something that's not showing the shadow.
There's a little bit of residual sunlight from sunset, so you can see that reflecting off one of the domes in the, not in the image you're seeing on your screen, but in the live stream. Tonight's image, this is from last night. The image you're seeing on your screen is from last night. Anyway, this is the annotated version, non-annotated version. And one of the things about using a laser guide star is every time there's a potential conflict with a satellite orbiting the Earth, we have to shut off the laser. So this was a moment when the laser was shut off, for example, right? You see the laser, no laser. If you look at the time tag, this was at 22:02:28. This was with the laser shut off, and this was a few seconds later that the laser was back on. And then here's the laser back on, but with the moon rising behind the Keck I dome. And here's a little bit later with the moon having It was in a little bit further, but now with the laser off, right? So the laser is on most of the night, but there are periods ranging from a few seconds to a few minutes, sporadically spread out throughout the night, when we have to turn off the laser to avoid conflict with satellites, danger of damaging equipment on the satellite, etc. And then here's a different view. This is using a different all-sky camera next to the, actually between the two Keck telescopes. You can see this railing connecting the two telescopes. The railing isn't curved. It just looks that way because it's a fisheye lens. This is Keck I. It's the laser shining towards the Triangulum galaxy. This is the arc of the Milky Way right there. This is Keck II at sort of 2 o'clock on your screen. And then at 8 o'clock on your screen, this is the Subaru telescope. So the Keck I telescope is closer to the Subaru telescope than Keck II. It's clear from this image that the Keck I is closer to the Subaru telescope. It looks bigger because it's closer to the Subaru telescope. So I'm just giving you a few different perspectives on that mountaintop. What is also cool over here is on the horizon, you can see the lights of, just man-made lights on the cities, city lights on the Big Island. And you can see a host of other telescopes at Mauna Kea here. They look much smaller because they're further away. They're also physically smaller than the two Keck domes, or the Subaru dome. Although the CFHD telescope comes close to being the same physical size, but they look small because they're further away from this particular location than Subaru. Anyway, I wanted to share these images with you. I'll cycle back through them again. This is the first image. Second, the same image, just with annotation, without the laser. Laser back on. Moonrise. It's a waning gibbous moon. Not quite third quarter moon yet. And you can't see the details of the moon. It looks like a blob because it's so bright. It looks circular, but it's not. It's close to a third quarter moon. And these artifacts over here, these are reflections of this bright moonlight off the camera optics. Even the thing over here. And this is again the Keck all-sky camera. Not the Subaru all-sky camera, but the previous images were Subaru all-sky camera. This is the Keck all-sky camera. And again, the image quality isn't great because I've used my phone to take pictures of the monitor on which these images are being streamed. Okay. Any questions before we move on? Let me stop my screen share.
I want to make a comment. You would have been so proud of Sonny today because we showed the pictures and Sonny did an incredible job of explaining them. You would have been really proud of him.
Sunny, well done. Very well done.
And the person who's logged in under my name, you can go in and change your name. So whoever this other Victoria Newberry is, I'm guessing is one of my students, just go in and change.
If you click on the three dots, there's a rename option. And once you click the rename option, you can change your name. In fact, if you tell me your name, I can change it, Vicky, if you...
Yeah, if you could type, you can go over to where it says chat and say, I need to change my name and tell me who you are. I have Tepoy and Taylor and Xavier and Des and Sunny and one mystery guest. Thank you, Rasha.
Of course. And Sunny, thanks for doing that. That's great.
Sunny really did do a good job explaining.
That's great. Sunny is a seasoned astronomer now after spending a summer doing SIP. Sunny, how was your SIP experience? Science internship program experience this past summer?
I'm not gonna lie, like actually doing the work and having to learn like how to code and whatnot was kind of stressful at first, but with the help of my my colleagues and my mentor, I was able to grasp a little bit of how to code and all that, and I was able to give my share to the project.
And you work with Max, right? Max Gogan.
Yep, I worked with Max.
Max is an undergraduate at UCSC. He's a third year undergraduate at UCSC. And he's also learning to code, but he was a very good mentor, I thought.
Yes, he was very open to much of our ideas.
And I don't mean to put you on the spot right now, but I can, at some point, I'd love for you to tell the group about what research you did this summer. It's actually related to the kind of research we're doing tonight. Right. Whose name am I? Oh, thank you, Aina. You've changed your name already. Thank you. And we're a small group again tonight. So I would love for people to pick up, that's okay with you, for people to unmute and ask questions. We're a small and manageable group tonight. We're always manageable, never rowdy, of course. I know which grade are you in? And I haven't had the, I'm going to see all of the Arcola students in person tomorrow, I guess. Tomorrow starts in a few hours, I guess, but tomorrow morning. I'd love to hear from the Arcola students. Sunny, thank you for, again, thank you for introducing the images or explaining the images. I'm putting people on the spot, but is that okay, Vicky, to ask?
Yeah, it is. I would say, I think a lot of our kids log in on a phone or an iPad where it's hard to do, to do their photo, to do the video.
That's
But
okay.
Taylor, Xavier's already spoken. If you could go around, kind of unmute and go around and just say your name, what grade you're in, and just say hi. Taylor, why don't you have a go? Unmute. Taylor, unmute and say hi. Go down to the bottom where it says audio, unmute. No?
Thanks,
There you go.
Vicky. Thanks, Vicky.
Say hello. You're on mic now, Taylor. Say hi. And what grade, Taylor? Well, somehow I'm not hearing you. Taylor's an 8th grader. I talked to her
Oh.
today about SIP.
Oh, fantastic. Taylor, I'm not hearing your audio either, but try again, please, if you wouldn't mind.
Okay, Xavier, would you introduce yourself?
Okay. Do I have to turn on my camera though?
If you can, it would be nice so everybody could see you, but you don't have.
Okay. My name is Xavier. I would really like to go to the thing that's going to be happening, where you guys sometimes take students for learning over there. I thought that would be a really good experience. I keep hearing about it and I thought that would be cool. It's got me really excited and I'm hoping I can go to the meeting tomorrow after school.
And what grade, Xavier?
8th grade.
Okay.
That's
excellent.
wonderful. And Xavier, the program is called the Science Internship Program. And it's going to be an 8-week summer program on the UCSC campus. From 7 of those weeks will be in person. The first week is online. So those 7 weeks run from June 23rd to August 9th. And we would love to have you there. Taylor, you're welcome to apply too. 8th grade is the first time you can apply. And 11th grade is the last time you can apply. So you have 4 chances to apply. And Sherry, thank you for joining. If you wanted to take a moment to introduce yourself, that would be amazing. This program is very much about the people behind science. So we will talk about the science too, but Sherry, please take it away.
Hi, I'm Sherry. I'm a staff astronomer at Keck. And last night, I worked with Raja's team to help them set up their planning for their science observation. And my job Well, some if you were here last night, you've heard this. It's kind of like a ER doctor. So if anything goes wrong, whether it's software or hardware or observers have any questions at all, I'm the first point of contact. So usually after everything goes well, then I go offline, but I'm on call. So they can call me anytime for any problems. And then I will start troubleshooting and decide if I can fix it. If I cannot, then I'll go down the list and see who else to wake up in the middle of the night to help me with troubleshooting. Could be mechanical engineers, electrical engineers, or software engineer. It all depends. So kind of like ER doctor, right? Triage first, starting on my end. But no one's dying. No matter what happens, no one's dying. So that is a great relief. And the sun rises, so no matter how hard the night may be, it will end. And I just heard that you were saying about internship opportunities. When you're older, we have this program called Keck Visiting Scholar Program, which is designed for graduate students, usually later in their PhD program. So that in that case, they are done with all the coursework and all the exams, so they have more time and flexibility to come out to Hawaii to work with us at Keck. It could be engineering project, it could be science project, could be anything that we have a lot of useful things for students to do. And it also gives them a first hands-on experience with observing. Because these days, a lot of science programs are very big programs with multinational collaborations and using space telescopes. And with space telescope, you don't do a lot of observing yourself at all. You tell space telescope staff what you want and what you want them to do, and then you just receive data. Unlike Raja and Joel, sitting there in the control room and actually driving the instrument and then control the instrument what they want to do and fine-tuning some settings here and there. So it's a very different experience, and we want to give younger generation more opportunities to really experience what observing is like, is so-called the classical observing, rather than sitting at home and receiving data from space telescope. That's very cool too, but getting to take the data the way you wanted it is a completely different experience. And there's a lot more to think through because sometimes the weather could change or instrument could experience some difficulties, challenges. And so you have to be agile enough to come up with backup plans to, mitigate whatever problem that happens during the night. And I've heard other scientists saying that they publish their research result quicker if they took the data themselves because they suffered through it, they felt the pain. So I wanted to publish the data sooner than later. That's what I've heard. Yeah, do you have questions for me?
Really, thank you. I mean, I completely echo your sentiment. When you're in classical mode like this, you can make real-time adjustments, positive,
Yeah.
because of positive and negative factors. Like last night, the air conditions were better than average, and we decided that we could adapt our experiment because of that. And so these are those real-time kinds of things don't happen when you set in a recipe of observations to the space telescope. It sends you the data back. Maybe a year later, you can adapt and do a second round. But here, during the night, within the hour, you can make adaptations. I love that. There's the other aspect of coming to observe, which is sort of the all-in approach. You're leaving your office, you're leaving behind emails, committee work, teaching, and you go all into the experiment. And there's sort of that aspect of it that I find is very sociological aspect of completely engaging with the experiment. That's lost also when the data are just being collected. Anyway.
Yeah. Oh, I saw a question asking what happens if it rains. That comes to the pros and cons. At Keck, because we guarantee your time. If your research proposal is approved and you're assigned the nights, then you get those nights. But if weather is bad, then you don't get any data. Sorry, you gotta try again next year. Whereas a space telescope, they run the observations differently, and they guarantee data. If your research proposal program is ranked very high, they'll try everything to get all the data you need. But if you're ranked in the second tier or third tier, you may only get, say, 30% of the data that you need for your research. And it's incomplete, but then sorry, you just gotta try again in the next cycle, and hopefully you get enough data. So there is the pros and cons into different scheduling philosophy, I think.
Certainly the technology would get damaged if it rains. So your telescope sits inside a building. You saw that sort of dome-shaped building that has an opening that gets closed well before it starts raining. The moment the humidity gets to a dangerous level, you have to shut it.
Oh, and what's special on Mauna Kea and on this island is we have an active volcano. So rain is not a serious thing. We know what to do. We can. But when the volcanoes Mauna Loa and Kilauea were erupting, were very active, actually we had to monitor how much dust there is in the air and sulfur dioxide, because those can also damage our optics and the delicate, complicated instruments as well. And also earthquakes. We've had earthquakes at night too, which was all these interesting natural phenomena that can hinder observations, but kind of like flying, you know, if weather is bad, then you're delayed.
Yeah, most of this equipment is not moisture or water tolerant. Certainly the coating on the surfaces of telescopes are very fragile. They have to be protected, but there's a lot of electronics there. So you can imagine that it really has to be in a controlled, humidity controlled, temperature controlled environment. That's really important.
Oh, one thing I want to mention that Keck is different from a lot of other large aperture telescopes. A lot of other large aperture telescopes, they have a primary mirror cover. And so when in the morning before they close everything, they will park the telescope pointing up, straight up, but with the cover, you know, deployed, so their primary mirror is covered. But at Keck, we don't have a primary mirror cover. So instead of pointing the telescope all the way up, we actually point it sideways, pointing at the horizon. This way, the surface of the primary mirror is perpendicular to the horizon, and this minimizes any water condensation or dust or anything. So that's our safe mode. We don't have a mirror cover.
I see. And anything
Yeah.
falling from the roof, for example, any condensation, if it drips, having the mirror vertical means very low cross section.
Yeah. And we're careful about parking the dome. So on the dome, we have shutters, and that's how we got light. But the shutter is definitely not super watertight. So we're careful to point the telescope away from the shutter, the edges as well. So if there's any dripping, it'd be dripping onto the backside of the telescope. It could be dripping onto the floor, right? But it's to minimize any dripping that's gonna land on the surface of the primary mirror. So we're careful about that too.
One thing that's very special about tonight is we have so many people from the Hawaiian island chain on the Zoom call. The
Oh, very
majority
nice.
of the people on this call, right? I mean, we have, if you're from Molokai, raise your hand. Let's see, Vicky, Taylor, Xavier, who else? Taylor, you're from Molokai also, right? And who else? Tepo? Desi?
Tepoy and Desi also.
Tepo and Desi also, okay.
You can raise your hand if you can find that little logo. Thank you, Taylor. And Xavier, yeah. So good group
And
to, it's good to be, we used to do this quite frequently and then life got in the way. It's good to have that again. Thank you, young
I'm
people.
going to take the privilege of putting up my hand because I'm going to be visiting you, and I feel like I'm more than a guest on the island. This is my 5th trip. Tomorrow is going to be my 5th trip to Molokai in the last 2 years, so that feels like home, and you all make it feel like home. So, and we know we have Noor there from UC Santa Cruz, who's also visiting Molokai. So, it's very special because I know that, there's a good distance and it's not easy to get from one island to the other. I'm having to take a hop on Maui to get from Waimea to Molokai. So it's not easy to get from one island to the other. But at the same time, you're closer to Mauna Kea there in Molokai than I am in my home in California. So you have as much right, I guess, to be part of all the observations that go on that mountain as anyone. And so I'm very glad, I don't know if many of you on this call know this, but the Shadow the Scientist initiative was advertised by Ohana Kilahoku, which is an organization that Kalepa helped found before his untimely death. Sam King, Malani Neal, Amber Imai is now the head of Ohana Kilahoku. Heather Kaluna, my former student, was part of it. But through one of their mailings, Vicky filled out the RSVP form to say, I'm going to take part in Shadow the Scientist. And Vicky, I think in the comments section, most people leave the comments section blank. You had written, I'm going to be joining on behalf of a classroom. And something got into me. I emailed you to say, tell me more about the classroom. And that's how our association started. I remember I connected to your classroom by Zoom multiple times before our shadow session. That led to now what's going to be a 5th visit, in-person visit. So I think sometimes simple things clicking like that can go such a long way. We had 2 students from Molokai, from Ako'ola School in Molokai, come to the science internship program for the summer of 2023, Asriel and Hunter. And they spent 8 weeks on campus doing research. Hunter worked on wild dogs and pumas, and that was a project in environmental studies, but at the intersection of computer science and environmental studies. And Asriel's project was with me in astronomy, looking at a particular kind of spectroscopic data and how to make improvements in how we extract information from spectroscopic data using an IDL-based pipeline versus a Python-based pipeline. This is what Asriel worked on. And then last summer, Sunny worked on a project that he will tell you about, an astronomy project. But he did this remotely from Molokai. Anyway, this is a deep association. And I also want to point out that one of the others on this call, or 2 of the others on this call, Stephen and Rohit, they're both undergraduates majoring in astrophysics at different universities, not at UCSC. Again, Shadow the Scientist is not about UCSC. It may have started there, but it's not about UCSC. It's very much about connecting people to scientists, whether or not they're at UCSC is immaterial. Stephen is an undergraduate. Well, Stephen, I'll let you introduce yourself. Rohit, you should introduce yourself. You guys are at different institutions. Talk a little bit about the science you're doing for the benefit of the group here. And
Oh, I'm sorry to interrupt. I'm gonna hop off Zoom now to go back to the work zone.
Sherry, thank you.
But,
Thank you so much. And I'll
thank
see
you
you
for
on this
having
other
me.
Zoom.
And if you guys have more questions for me later, Raja can relay them to me. Okay, it's nice meeting everybody.
Thank you, Sherry.
You're welcome. Pleasure.
And what Sherry said is so important, that you are, as high school students, a couple of you, as undergraduates, some of the others, have gotten internship experiences. She's talking about late stages of a PhD program. You can do an internship at Keck Observatory. And think of how well you'll be positioned and prepared for that if you've already done this as a high school student or as an undergraduate. You'd write a very strong application because you'll know what internships are about, and you'll have navigated this at a young age. So many reasons to go out of your comfort zone and try these things. Okay, Stephen, take it away, and then Rohit, I'll hand it to you. Tell us a little bit about your project and so on. Go ahead.
Hello, I'm Steven. I am a fourth year undergrad at the University of California, Merced. I went to UCSC for the summer where I worked under Raja. I looked at 6 star clusters in the Andromeda galaxy and compared these clusters using Keck II, a ground-based telescope, and HST, which is Hubble in space, to see which one had better image quality. Along with this comparison, I've also made 3D models of my star clusters and had my 6 interns work with me on this project.
Stephen, do you have any of your 3D models handy?
Yes, if you give me one moment.
They're really cool. And let me just preface this by saying Stephen's reason for creating 3D models was very serious. It is to give access to visually impaired learners. How through touch and feel, you can get a sense for what a Hubble image shows or what a Keck image shows. You can literally feel your way to understanding what a star. He'll show you. Stephen, I was just talking about visually impaired learners and the motive behind the 3D models.
Yes. Funny thing is that I actually presented a poster today at the symposium at UC Merced on inclusive excellence, where I presented the 3D models. So I actually have some new models that you have not seen yet, and I was super happy to share with you. I first have a zoom in of Keck and Hubble, with Hubble being on my right.
Oh, wow.
And as you can see, Keck has a sharper point, which means that the image quality of Keck is way better than Hubble, which has more blockiness to it. I can hold this better.
Yeah, you can clearly see that.
Yeah.
Yeah, compared to Keck.
Those look like Mauna Kea and Mauna Loa, actually.
And then I also have a cluster in blue, green, and infrared light to show how the peaks of this, the peaks mean more luminosity. And as we look at this, we can see which star cluster has the most peaks, which is in infrared, meaning that this cluster is really old, which makes sense because this is a globular star cluster.
That's so cool. Are those Keck images you were just showing?
No, these are Hubble.
Those are Hubble. Okay. What 3 filters?
Blue, green, and infrared.
Okay.
I
So-
used 110.
475, 814, and 110.
Yes.
And 475 is the wavelength in nanometers. 814 is the
Yes.
wavelength in nanometers, and 1100 is the wavelength in nanometers of the 3 kinds of light. Thank you, Stephen. And this is your final year at UC Merced?
Yes, this is my final year.
Our laser just shut down. You can hear the. Okay. Thank you, Stephen. I'm going to hand it over to Rohit for a moment to introduce his multiple research projects. Rohit, feel free to talk about 1 or 2.
Hello everyone, I'm Rohit Raj and I'm a senior final year student at Juniata College, Pennsylvania. It's like on the other side, east coast of US, and it's far away from California, but I have been working with Raja from over 2 years, and first time I got introduced to astronomy research was through the Shadowing the Scientist session I did with Raja. It was in India, we did remotely from here. But that was first time I observed, like I saw cake and everything. It was so exciting. And soon after that, I started research and the research on Andromeda galaxy. It's the galaxy next to what they're observing. It's nearest biggest galaxy. And I was SIP mentor where I mentored 4 students that year. from different places, and it was exciting because it was new to me, also learning throughout the project and understanding the galaxy, how it looks, how the star moves in the galaxy, and looking at the beautiful pictures, but also having them explaining to them. It was a great experience, and it was one of the most impactful experience I had that led me to go back to SIP again last year, and I plan to keep going back until I can. But it was a great experience, and right now I'm researching on unusual stars. So one of the type of stars in the galaxy they're observing tonight, the Triangulum galaxy. It's the second kind of biggest neighbor galaxy to us, and these stars are, like, you might be familiar with supernova, where the star has a very violent death where they die by a big nuclear blast. So these stars are on the last edge of their evolutionary age. So they are about to go in, like, very close to on brink of supernova. So these are very exotic stars, hard to find, but once you find it, so that's why they haven't been studied too much compared to all the stars. We are more in numbers. So studying these stars really adds much value, and eventually learn about the process of formation of stars and how they evolve and they affect their around surroundings. Sorry, it's too late for me, so I'm blinking. Thank
It's
you.
1:15 in the morning for you, isn't it? Because Rohit's on the East Coast. So the kind of star he's studying was discovered by two astronomers named Wolf and Rayet. They're called Wolf-Rayet stars. They are much more massive than the sun. They can be 10 or 20, even 30 times more massive than the sun. And they have very short lifetimes compared to the sun. Very short, not compared to human lifetime, but very short compared to sun's lifetime. And an even shorter time spent in this Wolf-Rayet phase, the brink of explosion phase.
Yeah.
Again, even that is short in a star's lifetime, a universe's lifetime, but long compared to human lifetimes. They spend, what, millions of years, a few million years in Wolf-Rayet phase?
Yeah, usually like the whole star has like million at most, but anywhere in range between.
So it says it's trying to offset and waiting for AO.
And
to
Rohit,
close
you're
the
writing
door.
a paper on these
Yep.
stars. Do you have a moment to share your overleaf draft for a moment? I mean, just screen share, I mean? If you
Yeah,
have,
yes.
again, I'm putting you on the spot.
No, I'm more than happy to share.
And that is the
So what you're going to see is sort of the makings of a journal article, the sort of the early stages. Not super early. This work's been going on.
the longest flavor thing. The rest would be.
Yeah, Rohit's work on this project started less than a year ago, but it's really matured into what is now storytelling phase, how we report our findings. And we're working with some of the world's experts on these kinds of stars. Phil Massey has been a real pioneer in this field. You can see Wolf-Rayet stars in the Triangulum galaxy. This is the title of the paper. There's possibly going to be 1, 2, 3, 4, 5, maybe a sixth author, possibly. Oh, is that Violet?
Yes, she's hiding. She's
Sherry's daughter is making an appearance on Zoom.
let me let me turn off the background.
Hey! Hey, Violet. Whoa. Hey, Violet. We're waving to Sherry's daughter who's on Zoom, on the other Zoom. Hey. Those are very cool headphones. So Violet was here in person yesterday briefly. Now she's on Zoom. How old is Violet?
How old are you? How old are you? She's 8.
8. Wow. Another budding scientist. And so just to come back to this paper, Bob Williams is a retired astronomer. Douglas Crionfiglio is a PhD student and he's in his 4th year. Ben Williams is a faculty member at University of Washington, works very closely with Zhuo. There'll be other authors on this paper, very likely. Kim Caminero is one of the undergrads at UCSC who's been helping with this project. This is early stages. You can see there's a, reason I'm going through this with you, the real reason for this, I never had the opportunity to see a paper like this when I was the age of the Akula students. When I was Rohit and Stephen's age, when I was an undergrad, I didn't get to see this. So I got to see these papers for the first time when I was in grad school. And that's quite late because by then you should be writing these papers, not reading them for the first time. So it's very cool that some of the high school students in our program get to read papers. They get to be part of some of these papers. If, if the stars line up, so to speak. Okay. Our laser closure is over. We're coming back. Okay, so abstract introduction is where you set context. Can you scroll down a little bit, please, Rohit? Thanks. And then you talk about what kind of data we have, I suppose, after that. Yeah, Hubble Space Telescope and Keck. That's what we are using. We used a different spectrograph on Keck for that project than we are tonight. And then we talk about how to measure ages and masses of stars using something called Hertzsprung-Russell diagrams or color magnitude diagrams. And we have a section on crowding, I guess. That would have been probably earlier, right? The section on crowding.
Yeah, it's not added yet. Once we confirm with Phil Massey.
Will Phil, okay. That would probably will precede section 3, between sections 2 and 3. And then the spectroscopic analysis of the, and now it will be more than 4, right? It's at least 6. And possibly if we get some, once Doug reduces those data, we'll have possibly 8. And if we get any tonight, it'll be even more than 8. We have 8 already, right? We have 6 with Demo spectra.
Yeah.
And then 2 more with Demo spectra that we got at the end of September. And then references are where you cite other people's papers, because your work is never in a vacuum. That's, it is coding on the left side, Aina and Xavier, but it is code that is used to generate the kind of text that you see on the right. Not typical computer code for calculations, but it's something called LaTeX. I'm going to put this in the chat. It's called word processing code. And this particular thing is called, yeah, there you go. Jamika just put the link.
Yeah.
And this is something that most scientists get to use. You get to learn to use it. It's not difficult to use. But most journals require that you write your papers in this format, either require or recommend. But it's very convenient if you work with this interface that Rohit is showing, something called Overleaf. You see it's called overleaf.com at the bottom. There's actually even a submit button where you can submit your paper to the journal. I used that recently to submit a paper to the journal, and it walks you through the process. It takes this document, sends it off to the journal, all of this handled electronically, of course. Gone are the days when you print this out and send it to, send a paper copy to the journal. This is what they use for scientific articles all the time. Yeah, Xavier, that's exactly right. And then, okay. Rohit, this is your Wolfray project, and thank you for sharing this. All right, I'm going to share my screen. That's okay. talk a little bit. Vicky, did you want to add something?
Oh, I'm not on mute. I'm just really happy with the participation of some of my students. Wonderful. Exciting. Thank you. Thank you, Ina, Xavier, Desi, for jumping in. Any of the rest? No shame. There's
That's
no such
wonderful.
thing as a bad question.
I'm going to talk through this thing that you're seeing here in green. I want to give you a sense of how much of the sky we are looking at. We're looking at a very tiny patch of sky. Just to put this in perspective, the diameter of the full moon, which is a familiar object, the diameter of the full moon, or if it's a crescent moon, from one tip of the crescent to the other tip, if you drew a straight line, that would be the diameter. So that distance is half a degree. Now, 1 degree can be broken up into what's called arc minutes, just like you can divide an hour into minutes. You can divide a degree into 60 parts. A degree, as you know, is 1/90th of a right angle. You all know that 90 degrees is a right angled triangle. So you take a right angle, divide it into 90 parts. Now you've got 1 degree. You divide that into 60 parts. That's called an arc minute. And the word minute even means small part of, it comes from minute. And that's why a minute of time is called a minute. It's a minute part of an hour. And an arc minute is a minute part of a degree. And the second time you do that division, that is, you divide an arc minute, second time it's called a second, because it's the second time you're dividing. And an arc second is about how wide this green rectangle is, 1 arc second. Whereas the moon diameter is about nearly 2,000 arc seconds. So this is about 1,000th, a little less than 1,000th of the moon's diameter, or 1/500th of the moon's radius. That's how tiny a patch of sky we're looking at. That's the width of the rectangle. The length of the rectangle is twice that. So it's 1.6 arc seconds by 3.2 arc seconds is the size of this rectangle. And those of you who joined last night know that we were imaging this star cluster in Triangulum, but we had placed the star cluster over there, if you can see my cursor, on the right edge. So we're imaging a patch of sky that includes the cluster, but to the left of it. Tonight we're imaging the cluster and to the right of it. So together we'll form a square with a cluster at the center. Does that make sense? Yeah. Any questions about that, or about what I just described? Now we're doing 2 things that go beyond taking digital images like the one you see in that green window. 2 things that are different. One is we are correcting in real time using a laser beam. The picture you saw earlier of that laser beam is not just for a fun laser show. We're using that laser to create an artificial star, a spot, high up in the Earth's atmosphere, 90 kilometers, I believe, above the Earth's surface. There are sodium atoms from micrometeorites. The laser that we shine from here excites those sodium atoms, causes them to glow, so we create a spot. That artificial star we use to take images. Very frequently, we take images of that artificial star. How frequently? Well, 1,000 times a second. And we do this because that's how rapidly the Earth's atmosphere changes. So by taking rapid images of this artificial star, we can monitor how atmospheric turbulence is affecting the image of the star. You've all grown up with Twinkle, Twinkle, Little Star. What we're doing is untwinkle, untwinkle, little star. We're trying to undo the effects of the atmosphere in real time by taking this rapid fire images of an artificial star, one or more artificial star. We're actually doing this for the laser star and other natural stars that are out there. This is called LGS. This technique is called adaptive optics, where we're adapting a tiny deformable mirror in real time, we're making it equal and opposite to the effects of the Earth's atmosphere. So that technique was pioneered by folks in California and elsewhere. It was actually behind the defense curtain when it was being used to study during Star Wars. It was used to study satellites, enemy satellites, trying to read details of them but that technology has been declassified and is now used by astronomy to take sharp images of astronomical objects. So we're using an AO tonight, adaptive optics, using a laser guide star. You can also use natural guide stars. So that's called NGS-AO, natural guide star AO. And tonight we're using LGS-AO, laser guide star AO. And reality is when you use laser guide star AO, you use both laser guide star, you use the laser guide star and natural guide stars, you use both. Whereas when you're using natural guide star AO, you're only using natural stars, not a laser. So that's a twist to how we're imaging tonight, is we're getting much sharper images than we otherwise would have because we are compensating for atmospheric blurring. Now, a very good way, you've all seen stars twinkle, but a very extreme example of the effects of hot and cold air is if you're driving on a very hot day and you're looking at the road surface in the distance, it often looks like there's water on the road surface because of the way things are shimmering. That's light actually undergoing reflection, total internal reflection between hot and cold layers of air. So that's a very extreme example of light distortion. When we're looking at more subtle differences in temperature, as there are in the night sky, there isn't hot and cold air, but there's cold and colder air. And when we're looking not so low in the horizon, but up in the sky, the effects are more subtle, but it's still there and it causes stars to twinkle, it blurs out images, and we're undoing that blur. We're taking sharper images. The reason that's important for us is because we're looking down the barrel of the heart of a galaxy, the Triangulum galaxy. This blur of light here is not one star, it's multiple stars that make up a family. It's called an NSC, nuclear star cluster. Not nuclear as in nuclear bombs, but the word nucleus means at the center, right? You have a nucleus at the center of a cell. You have a nuclear family where there is, so nuclear can also mean the center of, that's, an atomic nucleus is at the center of the atom, that's why it gets its name. In this case, it's called a nuclear star cluster because it's at the center of the galaxy. And it's a cluster of stars, quite literally millions of stars make up a cluster, but they're in a tight amount of space. So without adaptive optics, we can't discern individual stars from one another easily. We get the collective light, but we wouldn't get individual measurements without adaptive optics. So second twist is we're not just taking one image. At any given instant, we're taking images in multiple wavelengths. That's what you see in the blue screen here. You're seeing spectra at every pixel on the sky. We actually have a spectrum. And that's been packaged in a certain way to create this sort of funky pattern that you see here in blue. But a good way to think of it is we have images taken at different wavelengths of light. So people talk about a data cube where X and Y are positioned in the sky. X runs east-west, Y runs north-south. But the third axis is wavelength. So at different wavelengths of light, we form images. And this allows us to dissect the star cluster by being able to measure velocities of stars, chemical composition of stars, temperatures of stars. So a spectrum is worth 1,000 pictures. If a picture is worth 1,000 words, a spectrum is worth 1,000 pictures. So spectrum contains much more information about the astrophysics of the object whose spectrum we're taking. Okay, that's a lot of words from me, but questions? I see a lot of questions in the chat, so let me scroll through. what are the white lines for in the blue picture? I hope I've answered that, Desi. Those are what runs from left to right is the intensity of the object as a function of wavelength. So when you take a spectrum, the most common example of a spectrum is a rainbow, where sunlight is being broken up into its violet, indigo, blue, green, yellow, orange, red. Here we are taking a spectrum, but not at visible light, in infrared light. The visible light goes from about 0.4 to 0.8 micrometers. Meter, you know what a meter is. You know a millimeter is 1,000th of a meter. You all have rulers with millimeters and centimeters marked on them. If you take 1,000th of a millimeter, that gives you a micron. So the wavelength of visible light is something like half a micron. So 1 part in 2,000 of a millimeter. And what the wavelength we are studying tonight is something like 2.3 microns. So you take a millimeter, divide it into 1,000 parts, and you take 2.3 of those units. And that's the wavelength at which we are conducting our spectroscopy. So the eye can't see those wavelengths, the human eye can't. And a normal camera devices that we have on our phones don't see that light either. So this is a special kind of detector. I don't know if Zhuo, is the OSIRIS detector Mercat tellurides, or what kind of device for are we using for OSIRIS, the detector? It's not Innsby's, right? They're Mercats, right? I've forgotten what it is. Yeah, we'll have to look this up. We can look this up. They're not, ordinary CCDs, silicon-based devices are used for visible light, whereas for infrared light, one uses these. The principle is similar. They're arrays, they're pixels. You can see these pixels in the green image. You can actually see the pixels right there, individual pixels. But it's I think the active substance is mercury, cadmium, and tellurium. So Mercat telluride. Let me double check this. But Desi, those are spectra. Those are what those white lines are. Yeah, why did we, Stephen, why did we split the field left and right? Because it's a rectangular field of view, and we wanted to get good radial coverage all around the cluster. We figured a square does that better than a rectangle, because if we have a rectangle and you put the cluster at the center there, you don't get as much radial coverage in X as in Y. So that's why we decided to map the cluster in this way. Yeah, it really is related to the instrumental limitation and to get more science by imaging a symmetric region around the cluster. Yeah, how much power does the laser beam have? That's a great question. Okay, and Rohit, you've answered that. It's a few tens of watts. Yeah, so the telescope in this case is made up of, the Keck telescope is made up of 36 segments. Each segment is taller than you and me. So each segment is 1.8 meters. It's shaped like it's got 6 sides, so hexagonal in shape, each segment, and there's 36 of these segments. I can certainly see if I can find a picture of that. Yeah, M33 does not have a bulge at its center, so it's not a surprise that it doesn't have a supermassive black hole. The closest it has is this star cluster that we're studying. And these star clusters are not necessary. There's debate as to whether they contain any black holes at all. If they do, it will be something called an intermediate mass black hole, not a supermassive black hole. Supermassive is millions to billions of solar masses, whereas intermediate mass is 1,000, few hundred per 1,000, even 10,000. So in black hole studies, there's sort of this missing link. People don't know. There's some debate as to whether intermediate mass black holes exist. We know that black holes exist up to a few tens of solar masses. Those can be explained from just the death of massive stars. And the most recent excitement about black holes of that mass have been through LIGO, the mergers of such stars producing gravitational waves. If we didn't know they existed before, we did know they existed before through X-ray binaries, where massive stars collapsed into black holes and they're swallowing material from a companion, emitting X-rays. That's how stellar mass black holes were sort of first really confirmed. And then supermassive black holes are seen at the centers of massive galaxies. But whether there's a missing link in black holes or whether intermediate mass black holes exist is a subject of active research. Vicky, yes, I realize it is quite late, of course, for all of you. So I've been trying to answer. Yeah, there's a strong correlation, exactly as Rohit says, strong correlation between a galaxy's, the mass of its central bulge, which is, a bulge is a central swarm of stars, where stars are swarming like bees in a hive, as opposed to in close, like marching band formation going around a disk. And one of the cool things that we've recently discovered in M33, this is in the last 2 years, it was first published in 2022, we have a follow-up paper in 2023, Miranda's writing another paper now, is we've actually detected a dynamically hot component for the first time at the center of M33. There appears to be some kind of inner halo there. But whether there's a black hole associated with that or not, it's completely up in the air. But there is a dynamically hot component of stars in the center of Triangulum. It's a minority component. Only 15 to 20% of the stars are in that component. The remaining 80 to 85% are in a, in this sort of disk, differentially rotating disk. Sort of marching band versus bees swarming around a hive. Those are the ways in which stars move in galaxies. The swarming around a hive is called a bulge, or if it's in the inner part, it's called a bulge. If it's in the outer part, we call it a halo. It's becoming clear that Triangulum has a halo. It's always been known that it has a disk, but the debate has been whether it has a central bulge or not. The halo evidence is very new. Measurements made in the last year with the Subaru telescope, also on Mauna Kea, the Japanese telescope. So Triangulum is a happening galaxy. There's a lot going on. I mean, I shouldn't say that. Triangulum is what it is, and Triangulum has been sitting there for billions of years. What's been happening is astronomers' attention has really fallen on this galaxy, including our groups. And when people concentrate on something and put their resources together, you learn a lot. And that's what's been happening. Yes, there appears to be a direct correlation between galaxies having a central bulge and a supermassive black hole. In fact, the mass of that supermassive black hole correlates very strongly with the mass of that central bulge. Why that's the case is a subject of intense study. Exactly why that correlation is so tight and why it exists is so is that just right an X-ray at the center? Is there an X-ray source at the center of M33? I don't know. Rohit, you were asking. I'm not sure that it's bright in X-rays.
Oh no, you said there's just a hot like body at the center.
Oh, not hot as in temperature hot, dynamically hot. What dynamically hot is astronomical jargon, for meaning stars are swarming rather than moving coherently in a disk. Dynamically hot just means high velocity dispersion as opposed to low velocity dispersion. Think well-ordered marching band versus completely undisciplined, drunken marching band, right? So, well, kids, you didn't hear drunken now. But, swarm of bees around a hive, how they move, each one is orbiting the hive, but they're not all swimming in formation. They're not flying in formation. Whereas when a marching band is going around a field, they're all moving in formation. So stars can take on one of these two forms, patterns of behavior. When we say dynamically hot component, it means this kind of swarming behavior, high velocity dispersion. Vicky, you'd be able to answer whether are students studying something called standard deviation in math?
Actually, Sunny, because Dara's doing the math.
Okay,
I'm doing Macbeth.
you are. Okay, excellent, excellent.
Sunny, are you there? Standard deviation, I would think so, at some levels of math, probably not some. There's a couple of 7th graders online, probably not.
Who haven't come across that concept yet. But there is a bar at the center of M33, very small bar. It's been found in HST images. You can sort of see this sort of linear structure in old stars. This is the work of Adam Smersina. It's a recently published paper in the last few years. Again, everything is happening around M33. And, you know, this kind of snowball it's not accidental. What happens is some group decides to put in a proposal. Let's say in this case, the group that Zhuo, Ben, Julianne, and I are part of decided to put in this big campaign with Hubble to study Triangulum. Initially, it was to study Andromeda and Triangulum. That's what FAT stands for, Panchromatic, Hubble, Andromeda, and Triangulum. But the time allocation committee cut out Triangulum. So we had to come up with a different T, so it became Treasury. And so, Rohit, you worked with the FAT data. So the time allocation committee gave not as much time as requested. So we only had time to image a portion of Andromeda, not Andromeda, a portion of Andromeda and all of Triangulum. So after trying for multiple years, Ben Williams, who's someone Zhuo works closely with, succeeded in getting time. And that's when the FATER survey was born. Panchromatic, Hubble, Andromeda, Treasury, Triangulum extension region. FATER is the study of. Now, once that happens, other time allocation committees say, wait, they've got all this great information from Hubble on this galaxy. This is a good time to give them Keck time to get spectra. So there's this sort of snowball effect. Once you start getting information of one kind, other resources start coming your way because everyone realizes that that combination is more powerful than the sum of their parts. And that revolution has been happening in Triangulum. It happened a few years before for Andromeda. And that's also not a coincidence. When people see all the gains made in studying Andromeda, they say, wait, let's now do this for another and different galaxy with different history, different past, different future. Let's try to understand this in the same level of detail that we've understood this. We know we can. We've demonstrated that these techniques of study work. So what you're seeing there is very much about the sociology of how science works and how progress gets made. We are, let me take a quick look at where we are in the observations. You can see that this is seconds counting up. And if you can do your math quickly, we were talking about minutes, seconds, and hours. You know that 600 seconds is 10 minutes or 1/6 of an hour. And what we're trying to get is overall, I time stands for integration time, how much time we're collecting light from this source. Our goal is to collect light for 15 minutes, 900 seconds, 899.92. And you can see it's about 2/3 of the way there. We're actually doing not 1, but 5 of these exposures. So 5 times 15, 75 minutes. And then we'll do another set of 75, another set of 75, and so on. The detectors tend to saturate after a while, so you can't just do a 7-hour integration or 5-hour, however long our half night is, 5.5 hours. We wouldn't want to do that in any case because You could be sitting on something for that long, and it's a satellite image goes through and ruins the whole exposure, right? So you want to break things up anyway. There are also in astronomy, often there are cosmic ray hits from high energy particles that can create, non-astrophysical hotspots on the detector. And those, of course, strike randomly at different pixels. So taking multiple images means you can look at anti-coincidence and get rid of those. So we're taking a series of 15-minute exposures through the night. So you'll see the scale bar going up from, you can see this is counting up in seconds there, 707, 708, 9, etc. This rectangle that you see on the left here, this rectangle is the same, is the same as, it's a cartoon representation of this rectangle that you see here in green. You're seeing a spectrum here where as a function of x, which is wavelength, wavelengths are marked in microns at the top. You're seeing the y-axis is intensity, how much the light is. And believe it or not, these sharp steps here, you see these two steps here, one more step here, these are produced by molecules in the atmospheres of stars. So this galaxy is this particular cluster of stars in this galaxy is nearly 3 million light years away from us. It's more than 2.5 million light years away from us, 2.7 million light years from us. We can see individual stars in that galaxy. Mind you, those stars are more massive than the sun, but not only can we see individual stars, we can take their light, and through analysis of that light, we can tell you what chemical elements and molecules are in the surfaces of those stars. It's quite remarkable. This is what, the spectrum is worth 1,000 pictures. It's because it contains so much information. It tells us about how much of these molecules are present, which in turn tells us something about temperatures of stars, because when stars are very cool on their surfaces, these molecules can form. We all know that if a star's surface is hot, those molecules dissociate, they break up by virtue of collisions between molecules. The energy imparted in collisions is enough to break chemical bonds. So the presence of molecule tells you something about the temperature of the gas in the outer layers of the star. So there's all kinds of cool information one can glean. Hard to do. That's why we need big telescopes. Hard to do this. Needs technology like adaptive optics, but the payoff in terms of information gained and what we learn in terms of astrophysics of these stars is just huge. If I took a spectrum of this star, it looks different than the spectrum of this this is the center of the cluster. This is an individual star right there. It's got a big cosmic ray or some kind of spike. You see this persistence of these two bands around 2.3 microns. I bet this is some kind of molecular, I don't know my infrared spectrum well. If this were an optical spectrum, I'd be able to tell you what individual lines, what these individual bands are. But you could see these two bands, these two steps, do you see that? One at pixel 100, one at pixel, what pixel number is that? Pixel 120. You can see that persistently throughout. Right? One at 100, one at 120. At each of these two tick marks, you see those dips. Rohit, you see this in the Wolf-Rayet star spectrum. In the optical, you see our absorption. This is, you can see it's covering from 2.29 to 2.4, pretty much 2.41 on the right here. It's covering a small chunk of the spectrum in the K band, so-called K band, 2.2 microns region. Vicky, I'm so looking forward to seeing you. I'm going to miss Angel so much when I visit, because Angel's been there each of the previous 4 times, but I know you're missing her a lot. But I'm so looking forward to seeing you tomorrow. I know it's only two days and 2 nights, but we'll make the most of it.
Yeah. Sometime we'll come back when we have time to get out to the beach again and do beach day, but
I think we'll hopefully get time to do that sometime during the day
It is
tomorrow, day after tomorrow, maybe. We'll see. Noor must have landed by now, right?
Yes, I haven't heard from Dare. I haven't checked other screens to
No
look.
problem. No problem, of course.
I am trying to, again, absorb all this incredibly technical information. And I hope students that are here, you understand that I don't get all of this, so I don't expect you to get all of this. But the more I participate, the more I watch, the more it begins to have meaning for me. Just incredible opportunity. So for those of you students who logged in, I'll see you tomorrow and we can debrief too then. I'm going to
Look,
share we have a fabulous library, and I know, Raja, you know that, of books, and it's time to share those out. So we'll do. And
I'm bringing my art portfolio with me, Vicky. So I've made progress on the portrait that you saw before. I've made quite a bit of progress. I'll bring that along. Hoping to
Excellent.
work on it tomorrow, day after. And you'll love Noor. She is just amazing. Her name means light, and that's so appropriate because she's such an amazing teacher.
Yeah. Stephen and Rohit, thank you so much for sharing. Really nice. I'm trying to talk, by the way, Raja, Steve has a daughter who's 13 now. I would love to see her go to SIP sometime and help her to make that happen.
When does she turn 13?
She's in Botswana, incredible young woman.
And when does she turn 14?
I think she just turned 13 not too long ago, so it wouldn't be this. So we
wouldn't
have
be
some
this
time.
coming summer, so it would be 26. You know, we would
Yeah.
love to make that happen. There are other students who are coming from other parts of Africa. We haven't had a student from Botswana yet. We've had students from Ghana, Lesotho, Egypt, Morocco. Let's see where
Lesotho,
else.
fascinating.
Yeah, we have partnerships with specific schools now. In fact, ENCO School and Star Leadership Academy, Zimbabwe. We've had students from Zimbabwe as well. We've had quite a cohort of students from Africa, and this is in the last few years. So we had 4 students from Ghana in 2023, I believe. So no, it's the popularity among students is growing in Africa. I know that we've had a partnership with Ghana Planetarium in Accra. That's helped. One of my colleagues spent some part of her childhood there, and that helped with this connection. Sometimes, you know, these are relationships of trust, as you know. Having Steve there, having his daughter come here would be a tremendous way to get students in Botswana involved. It would be amazing.
Yes.
We've had a regular participant in Shadow the Scientist from South Africa, Annalisa Euster. She's been a regular. We've had Shadow the Scientist sessions with students in Ethiopia. They haven't taken part in SIP yet, but it's a matter of time, I think.
I love the international aspect, and I love the idea of at SIP having it really be an opportunity for not just an exploration in a field of study, but for a cultural exchange and understanding. I mean, as a liberal arts person, that's critical importance to me. So
absolutely. And Vicky, one of the things we've done in SIP each of the last 2 years is we've had something called a global showcase, where students have talked about their culture, their home, their food, you know, music, whatever they want to, because we want students to show up with their full selves, and not, you know, academia for too long has said to people that you have to look like us and talk like us before you can be part of the academy, and that's just not right. And you know, changing that is as important as anything. So I'm looking forward to chatting with Steve about the possibility of starting the process.
Tembi is her name. THEMBI. Tembi. Anyway.
Okay. All right.
I will see you tomorrow morning.
Okay. And bye, Taylor. Bye, Vicky. Take care.
Aloha.
Aloha. Bye, Xavier. See you tomorrow. Bye, Taylor. Okay. going to see what else is going on this. Okay, so you can see that the previous exposure finished, and we're now on a new exposure. We are, where are we? So this is, you remember how I mentioned it's a sequence of 5? These are the, if you can see my cursor, these are the 5. It's a sort of a dot pattern. If you think of a dot pattern of 5 dots, you know, like the number 5 would be represented on the side of a die. 0, 0 is the central position. The offsets we're applying, these are in arc seconds, 0.05 arc seconds. Negative in X, positive in Y means getting the lower, you're getting the upper left corner. That's the second position here. That's also finished. Then plus 0.5 plus 0.5 is the upper right. Then we did the plus in X, minus in Y, so lower right. And now we're doing the lower left. So we're finishing this dot pattern before we do another set of 5 like this. In between, we'll go off about 30 arc minutes away, about full moon diameter away, to a blank patch of sky, just to monitor what the Earth's atmosphere is doing. We'll take a single 15-minute exposure there. The Earth's atmosphere is very active in the near infrared. It produces a slew of emission lines from OH and water in the Earth's atmosphere. And even though it's dry up on Mauna Kea, the upper atmosphere has enough water vapor that you get these very strong, these are called telluric emission lines. Telluric means associated with the Earth's atmosphere, T-E-L-L-U-R-I-C, telluric emission lines. The atmosphere does 2 things. It glows, but it also absorbs light, and we have to account for both of those things. So the way we correct for the glow is by going off to a blank patch of sky where there's little else other than the Earth's glow, no bright stars there. And so that accounts for the additive component, the glow of the Earth's atmosphere. And then to account for the, not subtractive, but the bite it takes out of, you know, it absorbs light. The Earth's atmosphere absorbs light. So that's called telluric absorption. So we observe a bright star that's featureless, or hot star that's featureless, and all the absorption features we see in it are caused by the Earth's atmosphere. That's used to divide out the effects of the Earth's atmosphere. So telluric standards are observed to correct for that. And this is a very standard part of doing spectroscopy in the infrared. So we've already observed 1 telluric standard. We observed some last night. We'll observe probably observe a few more. These are very bright stars, so that takes 5-second exposures to get their spectrum, as opposed to 5 times 15 minutes. As you know, magnitudes are a logarithmic scale. So these stars that we're looking at here are about 20th magnitude, whereas the telluric standards are closer to 5th magnitude. So there's 15 magnitudes of difference in brightness, and every 5 magnitudes is a factor of 100. That means these are 1,000,000 times, the telluric standards are 1,000,000 times brighter than the stars that we're targeting in M33. And so we can get away with very short exposures. So how will the data come out? I believe it's a good question, Rohit. I'm not sure. I have a few data packaged as data cubes where you have X, Y, and lambda. Intensity is a function of those 3 quantities. I think that's how this is packaged also. That's convenient because now you can go to a particular XY or a particular group of XY, that's a star, and you say, I want to combine all of their intensity as a function of lambda. That gives you a spectrum of a star. In a way, the packaging is not important as long as software can read it, but conceptually, it's good to think of these data cubes as RA, DEC, and lambda are the 3 axes. Intensity is a function of those 3 things. Now, one has to remove the Earth's atmosphere's telluric emission, divide out the telluric absorption. Once all of that is done, then you've effectively removed atmospheric signatures. You have to, the instrument has to be calibrated. So instead of pixel number, you get intensity as a function of wavelength, not pixel number. And so that's also been done. You can see that in this view. You can see that it's got wavelength in microns here, not pixel. You've got pixel number at the bottom, but you've got wavelength in microns at the top. So that means the mapping has already been made from pixel number to wavelength. And that's part of instrumental calibration. I'm just intrigued by these two absorption lines. There's a third one here at 240. Let's see if we can find that in the other spectra. Yeah, it's too noisy. Yeah, you can see it there, 240. It's right there. This is that feature. It's very strong in this, of course, this star, this 240 feature. There's also one at 320. See if you can see those in these other spectra. Not there, but in this one, we might be able to see it. Yeah, 320, you can see a little dip there. 240, you can see this dip here. There's two dips over here. I wish we could change the contrast on this. I'm going to try and see if I can do that. Yeah, that helped. Let's see a little more contrast. Yeah, you can really see these 1, 2, 3, 4 features, right? 100, 120, 240, and 320. You can see those features in this star. You can see it clear as day, of course, in this composite. 100, 120. This must be a bad column of some sort, but 100, 120, 240, 320. Let me see if I can change the contrast some more over here. Sure, I hope it's okay that I'm changing the contrast on this image. I'm just trying to see more detail.
I think the last data position, so you can see we see a lot more coverage of the core.
It's great, yeah, because it's to the right. This is doing the lower right. This, I think the second last one is the lower right. Now it's doing the lower left. What's integrating now is lower left. Box 5, last one of the box 5, yeah. And what the image we are seeing is the second last of the box 5, right? Because it's integrating the last one, second to last one. But it's really beautiful. Can I show you something here, Zhuo? So if I take a spectrum of this star, do you see how you see these dips at pixel number 100, 120, 240, so second tick mark, and 320. And you can really see that in the central part also. 100, 120, 240, 310. Sorry, 320. I believe these are some kind of molecular bands. You can see that from this part of the cluster also. 100, 120, 240, 310. Just under 320, this last feature. There's another feature here at 306, pixel number 360. I bet that is also real, because if I go here, I bet you can see that. Yeah, yeah, it's hardly changing. Those must be real. And the other fact is, when you go to these, they get much weaker because, of course, there's less light. So when there's less light, there's the absorption strength gets lower. So I'm convinced those are astrophysically. These haven't been telluric corrected, right? Not yet. Okay, so they could be telluric. Sky subtracted, okay, but not telluric divided. Okay. Let me try. Let me go even. Let me try to make the contrast here. Okay. So I'm making the contrast really ugly. Let's see what that does. Yeah. So these you can start to see. These are pixel. This hasn't been flat fielded also, right? This has just been subtracted. So flat fielding will remove this sort of pixel to pixel variations. presumably this is not one star, but multiple stars. Right, this central blob.
Yeah.
And we'll be able to see that once we look at. Have you considered using a photocathode to produce a spectrum? That's exactly how, I mean, so photographic methods were used to take spectra early on. With digital technology, CCDs in the optical are used as detectors to capture spectra, and these sort of Mercat Telluride and INSBE devices in the infrared are used. Richard, we've sort of moved away from photographic materials to digital devices, partly because of repeatability, greater sensitivity, and things like that, right? When you take I don't know very much about photocathodes. I remember studying them years ago, but I don't remember much about them in this application. Wow. This is beautiful. Surely the image quality is beautiful. Really fantastic. So Zhuo started a new set here that is, because this is 100%, you'll see it'll go down to 0 in a second. There we go. So this is a set 13, okay. 12 is just finished.
Yeah.
Okay. Will these next set of 5 be in exactly the same pointing as the previous 5, or slightly different, or almost the same, right? They're not changing anything, right? Okay. And yesterday, I know we did one set of 75 with the unusual pointing. How many did we do with the standard pointing like this on the left? Is it 3 or 4? I thought I remember 3.
We should have 7 frames in total.
7 meaning 7.
7 positions. 7 the little positions around the exact.
I see. Each one being 5 times 15?
Sorry, they just 7 times
15
15.
yesterday. Okay. 7 times 15 yesterday in the new position, but in the first position we did, that was 5 times 15. Okay. So, and there's a lot of overlap between those two. So, and
The central position much. So those highly
crowded.
highly crowded, the densest part we would have more.
Should have them in almost everything. Almost everything.
Then that should be.
And today we have 5 times 15 so far.
Yeah.
Okay.
Yeah, so far.
So far 5 times 15. Okay. No, that's great. If there's time, if these data are going very well and we have some, if there's dead time at the end, I would love to attempt one or two of the Wolf-Rayet stars, really short exposures for they're not as bright as the telluric absorption standards, but they're much brighter than these stars, much brighter. Taking 5 minutes, it would be, like maybe 2 times 150 seconds would be total of 5 minutes. You could do up, down, dither. After we do the blank sky, yeah. We should finish everything we need to do for this, and then at the very end, if there's time, we should we'd love to do.
We could go in the stats if we, for some of the position we can't finish, we can just end.
That'd be great. That'd be great. Yeah.
Okay.
This is good. We're getting very good data. Yeah, Stephen, it would be very cool to make a 3D model of this data set. Jamika, is there are there particular aspects of tonight's observing that you have questions about, or anything else you'd like us to touch upon?
For me, not in particular, although I think perhaps it would be interesting to hear a little bit more about OSIRIS.
Okay. Let me, I'm going to share my screen. I'll continue to share the screen, but what I'm gonna do is bring up the information page about OSIRIS a little bit, so that this is my first time using the instrument. So I want to make sure I'm going to the source.
I'll put it back in the chat. I shared it earlier.
You did, okay. Oh, okay,
but
okay.
I'll
Thank you, thank you.
so other people can get to it also.
Thank you.
Yeah, here we go.
And Jamika, I just wanted to a completely random question, but related to STS, is in the fall, are we averaging something like 10 sessions a month or 5 sessions a month? Do we know?
The average number of sessions we're having per month?
Yeah, just ballpark. I wanted to get it. I get the sense it's of order 10, but am I off?
Like 4 this month, 5 this month. We had 4 last month. We had a handful in August.
Because I don't just mean astronomy, I mean all kinds of sessions combined.
Yes, that's correct.
Okay. That's pretty cool. Okay, so I'm going to look for the link. You said it was earlier in the chat. I'm going to.
I just posted it there again. I couldn't find it.
Oh, okay, there it is. Thank you. Okay, what does it say? What kind of detector? Let's see if, where would that? Let me see. I'm not seeing too many details here, so I'm going to try a slightly different page. I'm going to go to my own Google search. Uh, I want to see what kind of detector. Technical pages, that's what I was looking for.
I just dropped a link to that page.
Okay, okay, thank you. I'm not seeing much here. I guess I don't want the troubleshooting page. That's not what I want. See if I can. Try something else. So this is the Hawaii 2RG detectors that are being used here to the arrays here. But what kind of instruments are those? Let me see. Not seeing this here. So Hawaii H2 will be replaced with H2RG. What they don't tell me here is what kind of detector, what kind of chemical deposition is used for these. I guess I can do a search for H2R, Hawaii 2RG. Let me do that.
Maybe more generally, Roger, you can tell us why OSIRIS, why this instrument is important for this kind of observations, because it is the first time you've used it, and but you've had done other research with different targets before and using other instruments. So why OSIRIS for this for what you're doing here in Triangulum?
Those two aspects that we talked about earlier, one of them is to use laser guides for adaptive optics, and the second is to do this data cube, 3D data cube, like X, Y on the sky and wavelength. So in a crowded field to get spectra of every star, that combination makes OSIRIS the ideal instrument. And indeed, these are MERCAD telluride detectors, mercury, cadmium, tellurium. And invariably, these infrared detectors have a visible, sorry, the V and visible got separated here, but this is, it's very standard for these infrared detectors to have a visible light detector on top, a silicon device on top. So that silicon thing is this piece here, but the active part is this teledyne imaging sensors, MERCAD telluride. So the two kinds of technology used for what is called near infrared astronomy. So between 1 and, in this case, 1 and 3 microns. So 1.2 microns, 1.6 microns, 2.2. These are 3 windows in the Earth's atmosphere where it doesn't, we were talking about how the Earth's atmosphere absorbs light. Well, in these 3 windows, it doesn't absorb all the light. It absorbs only at certain wavelengths. In between those, there are almost opaque windows where the atmosphere doesn't do a good job of transmitting. So these 3 windows are called J, H, and K, 1.2, 1.6, 2.2 microns. We're working in the 2.2 micron, the K band. So yeah, in fact, so let's see. Yeah, Mercat telluride is one kind of detector. The other is called INSBs, indium antimonide. Indium antimonide. Sb is the chemical symbol of antimony. So indium antimonide detectors were in use early on. Now Mercat tellurides are much more common from what I gather. I've worked much more at visible light than I have with infrared detectors. Of course, but here we go. Hawaii 2RG. 2048 by 2048 is the number of pixels. So 2048 by 2048. But the reason this is a rectangular patch of sky, there's a reason for that. It has to do with, should I ask, Zhuo, do you know why this is, it says this is, it's got a square detector, but why are we seeing a rectangular patch?
Oh, we're using the 15 millisecond play scale.
I
I think
see.
different play scales have the size of
Different sizes. Okay.
then according to, because in the exposure time calculator, you can select and see how that looks like in the on the sky.
The sky. Okay. Okay. I'm gonna close this window.
That was good. That was good too, Roger, though. Thank you for that. Just because it's a new instrument that we haven't really highlighted on Shadow the Scientist before. I just wanted to get it out there for others to understand why you're using this instrument, you and Joe and the rest of your team for these kind of observations.
And as you saw, it images a tiny patch of sky at once. So for doing something like a survey of the entire Triangulum galaxy or the Andromeda galaxy, this would not be a good instrument. But when we want to study a small part of it in great detail, this is a great instrument for it. So horses for courses is what it is, depending on what science we want to do, we'll pick an instrument. And this beautiful creature on my screen is Abby's new dog, Mia. Oh, I got to spend some time with last week. Lindsay and I got to spend some time with Mia. All right. Let's see where we are. So we're on the second of the dither positions, and it is finished. Just started the second one.
Well, we're at the end of our scheduled time, Roger, but I'm happy to make you host if you'd like to continue.
Sure, can stay on for a bit longer.
Okay, all right. I'll do that now.
Thank you, Jamika. Thanks. Hey, Rohit, in all of the papers you've been reading about Wolf-Rayet stars, all of the spectroscopy has been in the optical, mostly blue actually, not even very far to the red. The DMOS spectra go further to the red. So if we do manage to get a spectrum, even one, of a Wolf-Rayet star tonight, It'll be an interesting thing to see what it looks like in the K-band. And it not just that, it'll also be at very high resolution, spatial resolution, and we'll get a spectrum of every star there, not just of the Wolf-Rayet star, whatever's in that patch. Now, the integration time will be short, so only the bright stars will have high enough signal to noise in the spectrum. But if there are other stars with emission lines, those will show up. What I don't know is where the Wolf-Rayet star emission lines are in that part of the infrared in the K-band. That's something I have no experience with.
Yeah, I
If,
can
for
start right now. Yeah, if there is anything on that.
for example, are there helium-1? We know that Wolf-Rayet stars have strong helium-1 lines, and they're not that frequent in the optical. We see like 5 or 6 of them, like 5876, 66, 6678. I forget all the wavelengths now, all the phone numbers now, but we see a few of them in optical. I don't know if there are any in the K-band. For example, I don't know if there are any Wolf-Rayet stars in this cluster. I don't think there are, because Zhuo was saying that this cluster is a few billion years old. It's not, it's not hundreds of millions of years old. If it's a few million years old, a few billion years old, it'll only have intermediate age stars. It won't have these very young or very short-lived massive stars. But we'll know at the end of this, in that 3x3 arc-second field, we'll see if there are any other Wolf-Rayet stars or.
Yeah, in the plot we made of like superposition of the Wolf-Rayet star on the galaxy picture, there are dots, but there's nothing exactly at the center. So
At the center, yeah. And remember, our patch of sky we're covering is 3x3. It's tiny. 3.2 by 3.2. It's very small. And in fact, for the if we get a Wolf-Rayet star observation, the patch of sky we'll cover will be 3.2 by 1.6. It won't even be 3x3. It'll be just a single pointing. What else are we looking at here? Yeah, OSIRIS is, or this AO system is a lens-lit array, not a slicer. Sorry, what am I saying? The IFU, OSIRIS is an IFU, is a lens-lit array, not a slicer. I'll have to look to see how the optics of this work. I don't remember how lens-lit arrays work for IFUs. But I believe what we're seeing here, these are this thing that we were looking at. Where is it? This active window, I believe these are all spectra.
So what's the range in micron of this instrument? Like where it 2.4, it goes to 2.4 or?
Yeah, it's from 2.3 to 2.4.
Okay.
So it's 0.1 micron, roughly speaking. You can see it's 2.29 on the left, and it's more like 2.41. So it's about 0.12 microns.